Thank you. Thank you so much. It's an honor to be here. And let's just begin just getting into some of the things, mainly in terms of what actually the malicious packet scanning that we are going to talk about. So one main thing that I want to make clear, but before I get in all of those, the jargonish, malicious, malware, vulnerability, CVE, it's been all there every time. But I wanted to understand how many of us are here, ProdSec engineers or AppSec engineers, try not to solve day in, day out vulnerability count, get it down, vulnerability management and all that. Great. So there are also, you've been hated by developers because you have been a blocker for a lot of people not letting their code bases successfully scan because of a lot of new vulnerabilities that they bring in. So I don't need to ask for how many of you are developers. So one of the things that we go for using the SEA scanners, there are a lot of node vulnerabilities, what OSV scanners, and many other SEA scanners, the software composition analysis. They have been doing all the known vulnerability scanning, but the supply chain attacks have been everywhere, and there is a lot of huge number of statistics is out there. What is going to be for supply chain attacks and how attackers are being so smart day in, day out. They're just finding ways to get into your software, not just from one point, through various entry points. And Salsa has a huge reading about it, but yeah. So the one I wanted to make clear about when I say malicious code here, I know vulnerabilities are also malicious code, but I mean malicious code is an unknown malicious code that are not being tracked or not being identified by the SCA scanners. So why am I saying this? The major problem when you have these vulnerabilities and unknown code part of you, if you have SCA composition analysis as an issue, you go with some SCA scanners and they get identified what are the dependencies that you need to update immediately or something that you need to change, what has security concerns for each. But when you have malicious intent code, where these vulnerabilities are not sometimes might not be maliciously intended, but these are very much intentionally being targeted to attack, and they've been smartly written and code obfuscated. Everything is out there where they have their own approaches to bring in the software, but how do you actually find them? So it's a huge topic, but this is an attempt where VET, an open source scanning tool where we have kind of various ways of trying to trying to find the attacking code base, the code lines and all of that. So two problems. One is that how do you find that? Another is where I told you the ProdSec engineers, this is not a common thing for them, where you have SCS scanners, there's a lot of repositories and container images that you have, and when you scan with different sorts of scanners, this number is so huge. So this is a real dashboard from Harness. So I work for security testing orchestration, which is a secure software delivery domain in Harness, where we see that whole dashboards which has a large number of issues. And now how much size of a team you need to resolve this, either for the developers or for the sec engineers. So right, but immediately it's not about my talk is not about how do you get this number resolved, but it's also about how you can actually fix those vulnerabilities that really matters, and how do you prioritize those important vulnerabilities that really need to be fixed. I know everything is important, but it's like having a lot of time bombs in this room, and you need to cleverly diffuse each. You should only diffuse those which gonna blast soon, right? So those are like, how do you prioritize each and every time bomb and diffuse accordingly so that you remain safe. But yeah, everything is a bomb, of course. So every of them are also bombs, but it's just that how you strategically prioritize and get through the approach. There are ways. One is also about, you can say, still. Scanner do provide you the critical, high, low, medium, but what about that? If you see the numbers, still they are high, and sometimes they are also kind of get out of the boundary, and it's too hard to manage all of them. So, why am I talking all this is also reason because most of the CVEs, like coming to a 78% of the images are actually not exploitable, even though sometimes differently they are categorized. But 80% of the vulnerabilities, some statistics here for the OWASP benchmarks, by Project JIT. The reason is when you have all of this part of it, you will see that many of the huge amount of efforts by the developers when you block them to fix certain of these vulnerabilities, which are not really affecting your code, you can potentially consume their time for asking them to fix that are not really kind of exploitable, or sometimes the alert fatigue and mainly the impaired prioritization problem. So why the problem? If you are aware, but in case just to give you a quick heads up, when you have your code, there are your direct dependencies and there are indirect, or we call as a transitive dependency. So each of these functions, what SCA performs, any of these scanners, they go through your whole dependencies based upon what availability your project repository has, a package locking system, and all of that. The scanner performs the direct dependency scanning, and at the same time it goes to the transitive dependency scanning and brings you all the data. The problem is, some of these functions or some of these code bases in the transitive dependencies are not being leveraged or not at all being executed, or not being even called in your real code, or the active application that you are working on. So when you have an option to prioritize vulnerabilities coming from the code lines that are being executed or are actually being utilized in the code, than to the one which is not at all being actively used, because the code is so huge everywhere. And the approach what we're going to look at is a static reachability analysis, where we'll be using VET to perform code analysis, and then that uses a tree-sitter algorithm to traverse and actually find those CVEs that helps you to prioritize. So that's where the VET comes in, an open source tool, as Ram introduced already. I just don't want to take much time, but that is one part of the problem. Another is where we look at the malicious package scanning that we spoke in the front. So to give you a heads up before getting into the demo, like how it all works. So it all starts with the CLI. Currently it's all CLI driven, where you actually scan the repository or the image, and then it performs the dependency mapping through the manifest or the graph that it generates. Then it goes to the metadata enrichment by various sources. So VET also contributes to it reports vulnerabilities to the OSV database as well, and it goes through the OpenSS scorecard. It has an integration, brings all the data together to put right there. Then you have code usage analysis, the fourth one. That is the one what we'll be looking at, how it performs the code analysis and how it can help us. Then you go for the risk assessment, the malicious scanning, that will come in a side. But there is one more thing which is about policy evaluation and reporting, where now you can actually have the scanner itself will help you to put out set of policies, whether to block or not, to continue the pipelines, or even anywhere that you have configured. So these policies can range from just saying out the criticality of the vulnerabilities, or even being the severities. I'll show you if you're interested about the policies, but out of the context. So how do you do it? Quick 2 steps. One, you actually perform the code analysis, and then you perform the DB. So this is the approach currently, which can be used with the VET. You actually generate the code analysis DB and then perform the scan. So to quickly show you, I want you to notice the top screen here. I just performed a VET scan -d. I'll zoom it a bit. So this will go ahead and actually performs the scan, and when you go for it, gives you your top 5 libraries to fix. These are just top 5. It doesn't mean the whole list of libraries. They are just the ones which the filters in VET has decided to show you. These are the 5. When you go for it, you will be having tags about in this way. But essentially, what you see is the impact score, vulnerability score, all of the risks are coming from the VET. But this is a generic scan that you can do with VET on your artifact or your code repository. But when you go forward and actually perform the DB analysis, like the code analysis part, and then you perform the code scan on the DB by using this command, and then when you go forward, you will be able to see some of these things are particularly tagged, saying this specific package has used in code, and then some are really not. So when you go in a larger scale, like the number that I've shown you, when you get this opportunity to actually see the vulnerabilities that have been actually loaded or used in your code, that's an immediate point to prioritize and actually address them, than to those that are not being utilized. So if you see that, one quick example is the impacted score here is more opinionated at this point of time. But at the time when you have 22 for the one which has this specific library, and then there is a little lesser score for used in code, you can rather prioritize this one than to this one, right? So that's how you kind of tend to be more giving more contextual around the problem and then identifying it. So yeah, this is how you can quickly do it, but you can read through more on how do you find out, but I just wanted to give you a heads up on how you perform it. So that was the demo. But then, so I've just kept a video ready in case if there's any issue. Yeah, this is what I was talking about when you have the used in code as attacks to go through in the analysis. So the malicious packet scanning, this is the part where you have, as you perform the code scanning through the analysis, you have an option to actually add a flag which says malware to the wet. And once you do that, the code and the whole package logs and all the dependencies are being taken to a free-to-use saved up cloud, because a continuous evaluation needs to happen. So I'll show you a quick example which I have opened in a new, the next tab. So right here, if you see, this is wetpkg.dev. This is a place where you can actually evaluate some of the packages, but mainly the thing this is built is potentially to showcase how the malicious, active malicious scanning is happening through the wet cloud. So when you go for a sample package, you should be able to find details about the OpenSSF scorecard which have been aggregated. But more importantly, if you go for malicious package scanning, you should be able to find the things that have been scanned and the available versions at which you can find which are actually being affected. So the quickest way to go for it is actually getting into the package analysis right from here. This is a real-time data which is being quite updated time to time. But when you apply filters and actually look only those which are malwares, you can even get in for further details about the packages that have been released to NPM or any package registries, or how it is the way it configured is whenever there is a package released to NPM and any other package registries, this thing get executed, takes back, it applies all the the package scanning on top of it, and then gives you some of the heuristics. It follows a Yara rules, the one which I was showing before. So it applies Yara rules and some static code analysis, and at the same time it also leverages LLM-based approach to understand the thought process or some sort of approaches that the attacker is trying to bring in with. So there are some studies in wet blog as well, which I found really interesting. This is the one which, when you look through the obfuscated code, you will be able to see how cleverly they are using and starting to create domains inside the things and starting to navigate the traffic and just executing the command from the remote side. But more importantly, after you have it, so the way how you leverage this part is just you just require some sort of an authentication with the cloud, because it's a continuous process happening. And then once you initiate the scan with the command with the malware, and then it goes to the free analysis which happens in the cloud. Then you have the malware AI detection. Then it actually goes for the GitHub action which you can leverage. So there is a shipped GitHub action that you can leverage when you are actually performing a PR request and you are raised a PR. This is going to go analyze your code base with the one in the database that have been stored as you have used it. So then it immediately blocks if there is any sort of malware identified throughout it. So this is an example of how it's been shown. So this GitHub action, when you get in detail, if you expand on malicious package, you can clearly see this is the one which is found malicious, and from there you can get in through further details about the NYC config, this specific package in this case. So the flow goes like this. You should, ideally the current approach is such that it's all been built, currently being experimented and tried out in various ways. But the way how you go through it is initiate the scan, and then that be taken to the cloud for the analysis, and then you have the action to be integrated part of your CI pipeline, and then once you have it, that gets identified and blocks your pipeline, and further you can do the analysis again and remediate or even exempt, and then come back and then address the following things. So this is a generic workflow that you can follow up with the malicious packet scanning with the wet. And then there is one more thing where we can talk about saying, so we can talk about saying how you leverage the static analysis with that and the malicious packet scanning with this malware tags. But this is one interesting thing that you can also look around is PMG, which is a packet manager guard, which allows you to actually block the installation of the libraries on the install time itself. So when you actually try to install, I wanted to show the bottom screen. So I'll just move it to the top. Yeah. So if you see this one, I tried installing, this is the way you use it, the PMG verbose and npm install request. So this library is quite safe. So what happens is when you have this PMG configured in your system and start to install it, it goes around and actually tries to go back to the whole analysis that it's been having in the cloud, and then comes back and says whether it's safe to go or not. But there is a case where you have one more. Yep. I'll just take a minute. Then you have one example of it where you just try to install PMG, try to install Express Cookie Parser, which is an impersonating the original one for a potential attack. When you have it PMG, it immediately blocks it. So this is a demonstration of how you can actually leverage and use this open source tool to actually block some of the attacks within the install time. So yeah, that's pretty much it. But yeah, a quick summary on what we were looking through, some SES scanning and code analysis along with the landscape, and from malicious packet scanning with PMG. So thank you. Thank you so much for listening. If there's any questions, I'll take it on. But I'm sure we have lunch, so I can be offline to take your questions too.
Yeah, so we'll cut questions short in the interest of time, but thank you so much, Teja, for coming here.